We begin today with the following. For integers a and b, let's prove if a is even or b is odd, then a times b plus 3 is even. We see this is of the form p implies q, and we will prove this directly. But you see, the statement p is an or. So let's think about this for a moment. How are we going to go about this? Let's see. Let's use letters S and T and remind ourselves about the or. We have 4 possible inputs. S and T can both be true and false, and the or is only false here. The or is true when S is true, or when T is true, or when they're both true. Now, if we think about this truth table, and then this P itself is an or, and in my specific example, A is even is the S, B is odd is the T, for instance, and then this S or T is my statement P, right? But I need to assume case 1, A is even, and that would cover either one of these, really. But you see, that's not everything, because the or is also true here. So case 2 will be, we assume B is odd. And then we have covered all possibilities for when the or is true. This is how this proof will go, and it is a proof by cases. Case 1, we assume A, B are in Z, and A is even. And then I need to show this A times B plus 3 is even. And in this case, there exists K and Z with A equals 2K. Then A times B plus 3 is 2K times B plus 3. Well, we see it here. It's 2 times an integer, which is even as K B plus 3 is in Z. So we have covered case 1. Now, case 2. This was the other possibility for when the or was true, and that is that B is odd. So we assume A, B are integers, and B is odd. And then also in this case, I need to show A times B plus 3 is even. Then there exists Y and Z with B is 2Y plus 1. We have, now let's work with this A times B plus 3. A times B plus 3 is, it's A times 2Y plus 1 plus 3, which is A 2Y plus 4. Now I need this, I want A times B plus 3 is even. So what I want is 2 times an integer here, and I'm almost there. This is 2ay plus 2, comma. Now this is even because this a y plus 2 is an integer. We have shown both case 1 and case 2, so therefore we have what we want to conclude, which is A times B plus 3 is even. And this completes our proof. This is a proof by cases. Here's another example where we want to really think about cases here. Now, as I have written this as a P implies Q. So this is an implication, and in fact, we will prove this directly. Now, If you try to just begin and let's do, so proof, let n and z, and this was the only assumption I have in my statement P. Okay, well, how are you going to get your hands on 1 plus minus 1 to the n times 2n minus 1? I want to show that it is a multiple of 4, or equivalently that 4 divides this. You see, depending on whether or not n is even or odd, minus 1 to the n is either 1 if n is even or minus 1 if n is odd. And so we really, or that suggests that breaking this proof into cases based on n being even or odd could help us. And something you can use is that every integer is either even or odd. Okay, so let's do this. Case 1, n is even. Well, in this case, there exists, say, x and z with n equals 2x, but also, so and minus 1 to the n is 1. Okay? Then, what do we have? We have 1 plus minus 1 to the n times 2n minus 1. This is 1 plus, this is just 1, and then we have 2x minus 1. Now, if you look at this expression, this is 1 minus 1, which is 0, and then we have 2 times 2x. This is just 4x. And then, as x is an integer, we see that 4 divides, well, this. And this is exactly what I want to show. That means that this expression here is a multiple of 4. Case 1 is done. We have shown the case where n is even. Case 2, n is odd. There exists y and z with n is 2y plus 1. And we also know minus 1 to the n is minus 1. 1 plus minus 1 to the n times 2n minus 1. This equals, well, this is 1 minus, we have 2y plus 1 minus 1. Now I just need to work with this expression. This is 1 minus, this is 4y plus 2 minus 1, which is, well, now this is looking very nice. You see, this is 1 minus 1, which is 0, and then we just get minus 4y, which is 4 times minus y. Now I have this written as 4 times an integer. So as minus y is an integer, 4 divides this expression, 1 plus minus 1 to the n times 2n minus 1. One more. This completes case 2, and maybe I will just end with a closing statement. Therefore, we have proved both cases, which tells us 1 plus minus 1 to the n times 2n minus 1 is a multiple of 4. And this is what we were trying to prove for any integer n. Sometimes proving an implication directly, as we have been doing, creates a challenge. And what is an example of this? Well, let's say for n and z, if 3n squared plus 1 is even, then n is odd. This is an implication. We see P here, and we see Q. Now, let's think about why directly here would create a challenge. And I won't start the formal proof. What I will think about is side work. This would be how I would work through this, thinking in advance. Well, 3n squared plus 1 even. So I would have in my proof, this equals to some 2k, where k is some integer. And then I want to get n is odd. I have 3n squared is 2k minus 1. And then, here, well, how am I going to get n as 2 times an integer plus 1? I have 3n squared is 2k minus 1. You might think divide by 3. This is a problem, but even that, there's more problems than that because I have n squared. And to get n, it will involve taking a square root. And if you take a square root, there's no guarantee the square root of an integer is an integer. Square root of 5 is not an integer, for example. So just thinking about my side work of trying to prove this directly, I realize this is going to be a challenge. Okay, well, let me erase my side work, and we can discuss another technique. And this can be quite often very useful when a direct proof seems complicated, as we see here. Well, let's go back to our logic discussion. And when we are talking about logic, we have the implication, P implies Q. And this is logically equivalent to not Q implies not P. This we discussed back in our logic lessons. But even if you don't remember that, you can show this logical equivalence using a truth table, for example. This over here was called the contrapositive. This is, well, okay, this gives us a proof technique. So when proving directly, assume P is true, show Q is true, is challenging. Sometimes it's easier to prove the contrapositive. So in a proof, and this is called proof by contrapositive. In a proof by contrapositive, well, we assume not Q is true. And then we work to show not P is true. And when we do, we have proved the contrapositive here. But because of this logical equivalence, we have, in effect, proved the implication. And, well, let's do this pink example as our first proof by contrapositive. This was our P, and this was our Q. Or this is our P and is our Q. And we want to prove by contrapositive. You need to start by either just stating the contrapositive, and so that gives the reader some idea of what you're about to do, or state that you are using contrapositive. And in this case, I will state what I will assume and what I will show. So let's assume, well, n is an integer, and I assume not Q. So I assume n is not odd. This means n is even. And then I want to show, well, not P. So I need to show that 3n squared plus 1 is not even, or equivalently, 3n squared plus 1 is odd. And then I will have proved this statement using contrapositive. Well, there exists x and z with n is 2x, and then we have 3n squared plus 1 is 3, 2x squared plus 1. This is 4 times 3 gives me 12x squared plus 1. And you see I have 2 times 6x squared plus 1, which is odd. because 6x squared is an integer. And this completes the proof. Maybe I'll just say thus 3n squared plus 1 is odd. And I am done by contrapositive because I stated what my assumption, I stated what I needed to show, that I was using this technique, and then I showed it. So this is a proof by contrapositive. Here's another example. For integers a and b, we want to prove if a plus b is greater than or equal to 15, then a is greater than or equal to 8, or b is greater than or equal to 8. This is a P implies Q. And if you try or think about proving this directly, it's kind of hard to get your hands on something. All you know is the sum is bigger than or equal to 15. And then what do you do with that? So we will use contrapositive. Maybe this one, because Q, you see, is an or. Let's state the contrapositive separately before we start the proof. So the contrapositive here of this P implies Q would be not A is bigger than or equal to 8, or B is bigger than or equal to 8, implies not A plus B is bigger than or equal to 15. Right? This is the contrapositive. It's not Q implies not P. Well, now, you wonder why we spent all this time on logic and negations. And, well, here it is. It's all coming back. Because we negate an or. This becomes, on this side, well, first you negate this. If you negate a greater than or equal to, it says that A is like this, less than. And then the negating an or turns to an and then we would also have B is less than 8. And this would imply, okay, again, you negate a greater than or equal to. This would say A plus B is strictly less than 15. So this is what I want to prove. I will assume it's an and. So I assume both of these. And then I show that this is true. By contrapositive, we assume A, B are integers, A is less than 8, and B is less than 8. If you're an integer and you're less than 8, then you are less than or equal to 7. Now let's just add. We have A plus B is less than or equal to 7 plus 7, which is 14. And this is strictly less than 15. Therefore, well, for integers, A and B, if A is less than 8 and B is less than 8, we have A plus B is less than 15. And this was what I wanted to prove. This was the statement of the contrapositive. And so this completes this proof. Next example. For an integer n, if n cubed is even, then n is even. Now this is very similar to, two examples ago, where if I start, we can just think about the proof for a moment. If I start directly, and I start by assuming n cubed is even, okay, n cubed is of the form 2k for some integer k, and then I want to show n is even. It will involve taking a cubed root to solve for n, and this is a problem. If you have an integer and you take the cube root, there's no guarantee, again, that you have an integer. And so proving this directly creates challenge. Let's again use the contrapositive. This is a P, and this is Q, and I will use contrapositive. By contrapositive, let's assume n is an integer, and, well, we assume not q, which is that n is odd. And then we want to show n cubed is odd. Okay, there exists x and z with n equals 2x plus 1. And now I want to say something about n cubed. I could multiply all this out, but since we have discussed counting and binomial theorem, we can just use that here. And if you remember the binomial coefficients for say 3 choose k, or the row in Pascal's triangle, it went like this: 1, 3, 3, 1. And so these will be my coefficients when I expand this. So this will be, well, let's say 2x to the 0 times 1 plus, we would have 3 2x to the 1 times 1, let's see, this was to the 3, squared, and then plus 3 2x squared times 1 to the 1, and then plus another 1 2x cubed times 1 to the 0. And then this becomes 1 plus 6x plus, this is 4x squared times 3. We get 12x squared, and finally we get 8x cubed. Right? This was binomial theorem that we recently did. And what am I trying to prove? I got so excited about the binomial theorem. Now let's look at what we're trying to prove. I want n cubed to be odd here. So I want this of the form 2 times an integer plus 1. Well, here I have a 1, and you notice I can factor out a 2 from each one of these. So this is 2 times 3x plus 6x squared plus 4x cubed plus 1. And this is odd as this 3x plus 6x squared plus 4x cubed is an integer. And this completes this proof using contrapositive. Let's do one more example using contrapositive. And we will see, this is also fun because we will prove not only contrapositive, but this will involve cases. And so it combines the two different things we discussed today. Well, this is definitely an implication. Here is P and here is Q. Why would I naturally think contrapositive here? Well, if you notice, P and Q are both statements that have a not in them. P is a does not divide B times C. And then Q has a does not divide B and a does not divide C. And it's much easier to work with the statement of divides, which is not P. And similarly, not Q will be a statement about divides. This is what makes me think contrapositive. So this one, because I have an and in my Q, I will state the contrapositive before I get started, maybe in purple. So the contrapositive here, which is not Q, implies not P. Well, this would say A divides B or A divides C. And this would imply here, A divides B times C. This is what I will show. And just like the very first example we did today, this is an or. So I will have to assume case 1, A divides B, case 2, A divides C. Okay. By contrapositive, assume, well, we have these 3 integers, and A divides B or A divides C. Okay, case 1. A divides B. Then there exists x and z with ax equals b. Now what am I trying to show? A divides b times c. Let's just multiply both sides by c. We have ax c equals bc, as here xc is an integer that says A divides this product. A divides the product. Now, the other case is almost the same. We're really just interchanging B and C, but I will still write it out, these two cases. In this example, the two cases are very similar. This says A divides C, and then I can almost run through the exact same argument with A dividing C. Now I have a y is c. I can just multiply just like I did here, except I multiply both sides by b. So I would have a y b is cb, and cb and bc are the same thing, as yb is an integer. We get that a divides bc. And in either case, we have shown what we want to show. So we are finished. Maybe I will state the original thing that we proved. If A does not divide BC, then A does not divide B, and A does not divide C. And we proved this using contrapositive, but also we had cases.